Everybody have a good weekend.
Yes, sir.
Any questions while we have a couple of minutes? Questions?
For the warm-up for HCN, the DUS, would it be 2 because the N deletes the H, so all that's left is a C?
Would the answer be what?
2 DUS?
For ACN, should be 2, yeah.
Because it just leaves the C and there's 4 spots and then 4 divided by 2.
I'd have to look at the math. Hydrogen counts as a,
It deletes the H?
from the formula.
Okay, so
So it's basically just C. 2n plus 2 is 4. There's none there, but this is 4. Divide by 2, 2.
okay.
Yeah. Questions about IR? Huh?
So on the workbook, it says draw the actively.
Okay. Whenever you ask a question, guys, make sure you speak loud so everybody can hear. Make sure like the person in the back corner can hear you. So always speak loud, guys.
Oh, okay, so my question was, in the workbook, you said draw the Lewis structure for the testing acetate, but isn't it ionic? So you just draw ion.
It is ionic, but it still has covalent nature to it. Acetate is a covalent ion. I mean, it's a mix. It's a, we're not turning those in here, guys. Despite what I said, and never turn anything up here, okay? Never turn anything in up here. So acetate has covalent nature.
Okay, also, it said something about degenerate orbitals.
Uh-huh.
I don't understand what that is.
That should be covered in Gen Chem, and if you look in any textbook, look in your Gen Chem textbook or Google it, you'll find degenerate.
I saw the definition, and it was like talking about p orbitals, but I mean, I couldn't fully understand what it was.
Show me your definition, because it's more than just p orbitals. You need to find a good definition of degenerate. Show it to me again, you'll find it. Okay, guys, top of the hour, we can get going. Any questions about the syllabus? Any questions about, yes?
I have a question about the lab. So it says that we're going over check-in, and usually sometimes there's a pre-lab to turn in, but for this one, we're just turning in the check-in when we go in. There's nothing to turn in before lab.
Correct. We're not doing lab this week. We're just checking in. After check-in, we'll have a lecture downstairs. Okay? Lecture as if right here. We'll make use of that time because time is very valuable. Check-in instructions are in the lab manual. Okay? Many of you have not purchased the lab manual yet. Lab manual is available upstairs, $15 cash only. Instructions are there. When you come to lab, no other instructions will be given. They're all there. You'll check in. We'll have safety overview, and then we'll go downstairs for lecture. When I say go downstairs, typically we'll go into a room over there on that side. E 1000 and or 1047 something. The smaller room over there on that side, east. That'll be our downstairs lab room. Was that clear? Anything else on that? Good. The lab, may have not pointed out last time, the lab schedule, of course, is on the daily schedule on the far right. Yeah. No lab last week, lab check-in, lecture, I'll check in lecture. So our first lab will be next week, which is what? Solubility testing. The handout I sent you over the weekend, physical properties, contains lots of the solubility information. Okay? I ask you to please print that and have it by Wednesday. We may get to it on Wednesday. I may refer to it, but we really won't get into it probably until Friday. IR, you're watching by video only. You're asking questions, working problems on that. Today we'll be referring to the functional group handout I gave you last time. You have the DQ page. First couple there you can be working on. We have our outline, green. We left off with like 2B. We'll do Lewis structures. Textbook. I assume everybody's got a textbook and you understand that you should be using your textbook. If you do not use your textbook, you will not do well in this class. Here's my textbook when I took organic. It's kind of falling apart now. It's Wade. Second edition. What's yours? Seventh?
Wave.
Seventh? Thanks. That was second. Cost $67, brand new. Still has the price tag on it. Okay, let's see where we left off at. Any questions? Everybody good? Everybody got anything here? We did a little structure last time for CH4O, yeah. How about the next one? How we do on C2H6O? Two constitutional isomers. Everybody know what constitutional isomer is, right? You look that up? Anybody give me a definition of constitutional isomers?
Formula of difference in activity?
Yes, very good. For C2, we can do H6O. We do two of those. Constitutional isomers. C2H6O. How many valence electrons are we dealing with? Each carbon 4, that's 8. Each H is 6, that's 6. Oxygen is 6. What's that, 20? 20 valence electrons. We got to make sure we have that many in our structure when we're done, right? Okay. Hydrogen's on the periphery. Let's bond the heavy atoms. How about something like, we got 2 carbons. How about C, C, O? There's 4 valence electrons. Let's fill up the valence of carbon with our available hydrogens. We can put how many H's around this carbon? 3. Carbon makes 4 bonds, no lone pairs. Standard bonding. Carbon is good. Octet. Let's make this carbon good. H. H. Do we have 5 H's? Oh, we actually have 6, so we got 1 more. Carbon's good. Carbon's good. H duet. Where do you want to put the last H? Just falls into place, right? Oxygen makes 2 bonds. Put the H there. 2, 4, 6, 8, 10, 12, 14, 16. Well, we're supposed to have 20. That means we got to add 4 more. 2 lone pairs. I'm not going to worry too much about bond angles. This is a systematic approach to drawing on Lewis structures, particularly for small molecules here at the outset. Again, once we get going, we're going to do even kind of quicker and more intuitive. The molecule gets too big, you're going to have trouble doing this systematic approach. Very viable thinking, though. Okay. Is that a nice structure? Anything wrong with it? You like that one? We don't have like 5 bonds to carbon, do we? Or oxygen with no octet. Does oxygen have an octet? 2, 4, 6, 8. Yes. Good structure. Could we have drawn another structure of this formula?
Yes.
Yes. Did anybody put together with COC? Something like this. And fill the valence of carbon here with, how many H's do we have? 6. Carbon makes 4 bonds. There we go. There's your 6 H's. We don't have another H, nor do we need another H, because that's 16 valence electrons. We can put 4 more up there as lone pairs on our oxygen, just like it needs. for standard bonding. Two different compounds here. Two different molecules. They have different physical properties. This one's, do we know a name of these yet? Functional group.
Alcohol.
Yeah, this is an alcohol. We'll look at functional groups. Okay. 2-carbon would be ethanol. We'll learn nomenclature. The F means 2 carbons, and it's an alcohol, OL ending. This is not an alcohol. It does not have the hydroxyl group. This functional group. Ether. Oxygen bonded to 2 carbons. This oxygen is only bonded to 1 carbon, and it has an H on it. No H on this oxygen. It's an ether. We'll look at functional groups in a little bit. This is called dimethyl ether. Because these are methyl groups. It's 2 methyls on the oxygen, which is kind of your ether starting point. Constitutional isomers. Okay? I didn't write it here. It's written right there. You need to know constitutional isomers. Any such thing we come across like that, you need to know. 2 good structures. Same formula. Different connectivity. Right? Here the oxygen is connected to 1 carbon. Here it's connected to 2 carbons. Different connectivity for these atoms. Yep. Both with no DUS. What is DUS? Degrees of unsaturation. Neither one of these have DUS. We'll look at that going forward a little bit more. So no DUS. It's written there. I'm not going to write it on the board. Not that it's something to memorize, but when you're looking back at your notes, you just say, these don't have DUS. Do I understand that these don't have DUS? Yeah, you can look at the structure. I was going to collect the pre-course questionnaire in the lab this week. It's easier to collect things there. Assuming everybody has it, please hold on to that. Some of you never put anything up here, guys. Among other things, that helps me just have them separated into sections. So please turn that in lab if it's not already here. Okay? Come to lab. Structures with double bonds. Already given it away there, right? CH2O. How many valence electrons? By the way, how do we do? Everybody get low structures of those over the weekend? CH2. Valence electrons. 4, 2, 6. What is this? 12? Is that right? Well, we only have 2 heavy atoms, so let's bond the C and the O. The H's go around the periphery there. By the way, I can look at this formula and tell we're going to have a double bond. Because I know the idea of DUS, degrees of unsaturation. That's a very powerful thing to do. Just looking at a formula, you can tell something about structure without even starting. But let's do it systematically. We got 2 H's. Where do you want to put them? Well, I recommend carbon. I'm not going to worry about bond angles yet. Okay. Uh-oh, I need another H here or something. I mean, I need a 4th bond to carbon, right? I don't have another one. Well, how many valence electrons? 2, 4, 6. I've only put half of them up there. I got 6 more I can put up there. Usually we always put lone pairs. So 6, that'd be 3 lone pairs, right? And we can start putting lone pairs now. And when you start putting lone pairs, I would recommend you put them on oxygen first. Fill the valence of oxygen first. Why? Because it's more greedy. It wants the electrons more, right? It's more electronegative. You gotta make the oxygen happy first. So let's fill the valence of oxygen with, how many lone pairs can we put? 3. Now I have 12 valence electrons up there. Does oxygen have an octet? 2, 4, 6, 8. Yes. How about the carbon? No. So is this a good structure? No. Typically you want all octets. Unless we say, well, you can't, or, but at this point, octet. Well, let's just throw another lone pair up there. Nobody will care, really. You only got 12. That's what this number means. You can't put another one up there. Well, let's put another H. Can't do that either, right? Here's what we need to do. We need to ask this oxygen. You really already shared one electron. We really just quickly got past that. We need to ask this oxygen to share more electrons. Okay? And we're going to do our first mechanism arrow of the semester. We want to take these electrons that I circled and move them in here and lay them in here and make a bond here with those two electrons. Turn that into a bonding pair between here. And what does this arrow movement give? Okay? This is called a resonance arrow. Double-headed. You never use this arrow for anything else. Doesn't mean equilibrium. That's a different. What does this arrow give? What does it mean to you? Somebody tell me. What do I have now? We now have another bond between the C and the O. This is two electrons here, and that's two electrons. These two electrons used to be a lone pair. We moved it in and made a bond. This is sort of the convention that we do on our paper and on the board. The H's are still there. Let's don't worry about bond angles yet. How many lone pairs left on the oxygen? 2, because one of them was moved in to make a shared covalent bond. That's what that arrow means, and you got to know what your arrows mean. Okay? What does arrow mean?
So on that arrow, because you drew it like double-headed there, do we need to put another, like, one near the electron?
Talking about here?
Yeah. Like
No, that's a resonance arrow. This is a mechanism arrow.
Okay, gotcha.
Shows what the electrons are doing. Mechanism arrows always show what electrons are doing. We'll talk plenty about this. Resonance arrow will define what that is. But let's look at the result. This is called convention to get us to this point. What do you think of this structure? Does oxygen still have an octet? 2, 4. Each bond, it's a double bond. We'll talk more about it. But each bond is 2 electrons. And the oxygen gets to count 2 of these and 2 of those. 2, 4, 6, 8. Oxygen has an octet. What about the carbon now? 2, 4, 6, 8. Now the carbon has an octet, and here's a good structure. It ends up having a double bond between the C and the O. I told you at the outset. You can also tell that from formula. And here is your best structure. I'm going to call it major, which kind of means best. But major is going to be, this over here is going to be minor. Today it's kind of bad because we're striving for octets. As we move forward, we'll find this kind of acceptable for some reasons as we learn more. These are called resonance structures. Okay? I'm not going to write definition here. Resonance structures only differ in placement of their electrons. Whenever we went from here to there, all we did was move electrons, right? If all you do is move electrons, you're doing resonance structures. If you start moving atoms, or removing or adding an atom, you're no longer doing resonance. All we did is move electrons, and we indicated that with a resonance arrow. These are resonance structures, much more coming. Charge. This is actually standard bonding for oxygen, which is what? 2 bonds, 2 lone pairs. The 2 bonds happens to be a double bond, but it's 2 bonds. Carbon, 4 bonds, no lone pairs. Standard bonding. Is this standard bonding for carbon? No. Oxygen. And what did I say if it ain't standard bonding? It's probably going to have a charge. Yes. So let's look out for charge here. What's the charge of the carbon? Now, formal charge was only a couple down, so hopefully you were looking at that over the weekend to prepare for today. What's the charge of this carbon?
Plus.
Positive. How do you know it's positive? Charges, we show the charge and circle the charge for me. How do we know it's positive? How do you do it?
Formal charge.
Formal charge. How do you do formal charge? Sure, there's a formula in your book.
The way I do it is normally I just count how many valence electrons are around it. So there's 3.
Uh-huh.
So in order to have 4 valence electrons, I just add.
Yes, it's missing one, right?
Yeah.
You count how many valence electrons. Now, when you do that count, you're not counting octet count.
No.
Because octet counting has 6, because you're shared. You're counting individual. How many did it bring to the dance? It brought 1, and that one brought 1, they teamed up, made the bond. It brought 1, that brought 1. In terms of what it brought, valence electrons is 3, in terms of that type of count. So it has 3 electrons. How many is it supposed to have according to the periodic table?
4.
And according to this, right, 4. It ain't got 4, it's missing 1. And if you're missing an electron, what's going to be your charge? Positive. Okay, how many did the oxygen bring to the dance? It owns its lone pairs, always. 2, 4, 6, one of these. Because the other one came from carbon. Okay? I'm going to call this own. Owns 7 valence electrons. How many oxygen is supposed to own? 6. So it's got 1 more than it's supposed to. And if you got 1 more electron than you're supposed to have, it's going to be negative. Also, for in organic chemistry, we show charges right on the atoms. We don't put it up here in the corner or anything. We got to know specific atoms. Okay. This is no charge. We can tell by looking at here. Because if there was a charge, it should have been shown at this point. No charge. Yeah, there's no charge here because it's balancing out. It's net neutral. And of course, that's going to be net neutral. There's no charge here. Carbon owns 4, oxygen owns 6. Nothing charged over there. So we need to know how to do charge. Okay, DUS. I erased, but let's go back to, well, I erased because that was Friday. On Friday, we drew a structure that looked like this, right? CH4O. A C and an O with 4 H's, C and an O with 2 H's. This is saturated. Saturated means max number of H's. If you've got C and O, you can have 4 H's max. And we'll say how you know that. Assuming you know that, you got C and O. Well, maximum H's should be 4. But you're missing H's. Okay? You're missing H's. Well, this is not well defined yet. This is going to be unsaturated. Okay? That is, it's not saturated with H's. It does not contain all the H's. And it turns out that, how many H's are we missing from saturation here? Okay. Turns out every 2 you're missing is called 1 DUS. Okay. Right now this doesn't mean a lot. This is just for your notes when you look back. 1 DUS, because it's missing 2. And 1 DUS tells you it's going to have, for example, 1 double bond. So I knew already that this had to have 1 double bond. So let's look at that a little closer. And I said it has 1 DUS. D, ACN. ACN has 2 DUS. How many double bonds is it going to have? How many? Why would it be 0? If 1 DUS is 1,
Wait, what, you're looking at CN4?
HCN.
Oh, HCN is a triple bond, so it's only 2.
Well, you're bringing in knowledge already. Let's approach it as if we were looking at a brand new problem on a test. You can't just bring, how do you know HCN how many, it has 2 DUS, I'm telling you. So how many double bonds is it going to have? 1 DUS is 1 double bond, so 2 DUS should be 2 double bonds, right? Well, the problem is, it's more than just double bond, it's really pi bond. And triple bond has 2 pi bonds. So really what we're referring to is pi bond. Well, let's look at it. Let's do HCN first. How many valence electrons in HCN? Carbon's 4, that's 1 is 5. How about nitrogen? 5. 10 valence electrons. Okay. Let's bond the carbon and the nitrogen. Put the H's on the periphery. Where do I put the H? I recommend carbon. Could you do it on nitrogen and get a decent structure? Yeah, you can in a lot of cases. But let's do this here first. I need more H's here. It's like, don't have a lot of H's. It's actually because we're missing some. This has 2 DUS. Based on it having 2 DUS, how many H's is it missing? Yeah, it's missing 4. I could have had something, first off, usually this is more of a formula, structural formula, because usually we list carbon first. CHN looks very odd, because this is telling you some information here. We could have CH5 in. That would be saturated, but we're missing 4 H's. Okay, let's put lone pairs. Where do you want to put them first? Nitrogen. Nitrogen's now good. 2, 4, 6, 8. How many we got up here? 2, 4, 6, 8, 10. Well, that's it. Carbon's in bad shape. It's only got 4 electrons around it. It needs 8. We don't have anything else to do. What do you recommend we do? We're going to have to ask this nitrogen to share. It may be greedy and not want to share, but we're going to make it. Let's take these electrons and move them in here. What does that get? All we're doing is moving electrons, so it's going to be resonance. We show resonance here. What do we have now? What's between the C and the N now? Double bond. And 2 lone pairs left. It don't matter where you put them. There's 2 there. 2 lone pairs. Are we good now? Finished? No. Carbon still doesn't have an octet. What do you want to do again? Well, let's say nitrogen, you're going to have to share again, buddy. Let's do another resonance structure. Now we have HC, what do we have now? Triple bond, and 1 lone pair left on nitrogen. How about now? Carbon have an octet? 2, 4, 6, 8, yes. Nitrogen, 2, 4, 6, 8, yes. Now we have a good structure. Standard bonding for nitrogen. 3 bonds, 1 lone pair. 3 bonds, 1 lone pair. Standard bonding for carbon, 4 bonds. We don't have standard bonding. And this is typical structure for ACN. Yes, it has triple bond. It's 2 pi bonds. Okay. 2 DUS. Right? We said that on the handout. 2 pi bonds, 2 DUS. For the good structure. How about charge? Did these ugly guys over here have charges? Atypical? Charge of carbon. 2 plus, charge of nitrogen. 2 minus, carbon. 1 plus, just draw plus. Nitrogen. How many does it own? 2, 4. One of these is 5, one of those is 6. It owns 6, but it's only supposed to have 5. So it's negative. See? Starting with this very actually polarized, shared. Now we share and it actually turns out all neutral. Okay? This is your best structure. That's your major resonance structure, etc. that fits the idea of octets for all your heavy atoms and duet for hydrogen. Correct number of valence electrons. Formal charge and how to determine it, well, we've already done that. Okay? Now in your book, you'll find a formula. I basically did a formula, but I didn't. Okay? You need to understand the formula. Okay? Carbon with 5 bonds? No, not on this planet. Although, well, you guys don't need to hear that. Silicon, can silicon make 5 bonds? Yeah, again, when you go down, you have d orbitals, you can start actually making more bonds. Sulfur can make more bonds. But the second row across, which is kind of what we're focusing on, and everything we say here is often done down here, but these can do other things as well. And whenever they do other things, we'll point out that it's odd. Let's look at the handout in the DUS page. By the way, this is kind of a functional group. Typically, with H here, it looks a little funny. Anybody know this functional group?
Nitrile.
Carbon triple bond N.
Nitrile.
Nitrile, also called a cyano group. Yeah, we'll look at functional groups as well. Let's look at DUS first. It's on the third page. DUS you can get to from formula, or you can get to from looking at structure. If ever you can't see, please yell it out. I'll assume you can see otherwise. From structure. We've already said this. One double bond is one DUS. Well, let's say it this way. This is triple bond. One triple bond is two DUS. Because really the DUS is pi bond. And as we'll see when we move forward and look at the next level of bonding, when we look at the orbitals, hybridization, you'll see that there's 2 pi bonds here. 2 pi bonds is 2 DUS. A triple bond has 2 pi bonds. So that's all there. In addition to your pi bonds, a ring is also 1 DUS. Now 1 DUS means you're missing how many H's?
2.
Right. To make a ring, you're going to have to remove 2 H's. That's why it ends up being 1 DUS. We'll look at that. Okay, ACN missing 4 H's compared to max. We said that. Let's look at what max would look like. Here's the CN bonded together. But if we just put all the H's up there possible, we can put 3 around carbon, and we can actually put 2 around nitrogen. And leave a lone pair there. And that's the correct number of valence electrons. So you see C and N can take 5 H's. And that's the maximum it can take. So where are we at on the side here? So for 1 C and 1 N, 5 H's is saturated. All right? This is saturated with H's. But if we got C and N and only 1 H, we know, and we're going to learn more about formula down here, we know we're missing 4 H's. And every 4 we're missing, every 2 we're missing is 1 DUS, so every 4 we're missing is what?
2.
Yeah. The number you're missing, you divide by 2 and you get the DUS. Missing 4, divide by 2 is 2 DUS. That tells us we're going to have 2 pi bonds, and indeed we do. This structure is saturated. No pi bonds. all the valences is filled with hydrogen. For 2 carbons, we end up with 6. But here, for 2 carbons, we only got 4. We're missing 2. That's a DUS. We also can tell because there's a pi bond here. It has to be to come up with a good structure. Saturated, this would be called an unsaturated compound. Also for rings, 3 carbons. The maximum number for 3 carbons is 8 hydrogens. By the way, how do we know it's 8? It's written here somewhere. I think it's right here. How am I coming up with 8 real quick?
2 plus 2.
If I didn't see structure, how do I know C3, what's saturated? 8. How do I know that? Because 2n plus 2. This tells you saturated number. Where n is the number of carbons. So if you got 3 carbons, what is 2n plus 2? N is 3, so that's 2 times 3 is 6, plus 2 is 8. Okay. 2n plus 2 tells you the number of hydrogens for saturated. From there, you can see how many you're missing. So, for example, if I had a formula that was C3H2, how many DUS? I'm missing 6. You divide that number in half, 3 DUS. That's all explained here. I'm working with formula. Formula is actually down below. How many DUS in the drug ibuprofen? This is just mentioning this. Okay, we got to start getting used to line bond structures. All right. These are all carbons. These vertices. Structure. How many DUS in this structure? We haven't done hybridization yet, pi bond. How many pi bonds are here? The second bond of a double bond is a pi bond. So essentially, how many double bonds do you see here? 4? 4. That's 4 pi bonds. Okay. See anything else that counts as a DUS?
The ring.
A ring. I know what a ring is. Circle, it's connected. Yeah? Got this 6-membered ring. That's a DUS. I see 5 DUS here, right? 1, 2, 3, 4, and then the ring is 5. There's not one out here that got cut off. Also, when I draw a benzene ring, my pi bonds may not be exactly blue. They're not going to be so precise. Benzene ring you'll see over and over. It's very common. And then you got the carbon double bond up here. Oxygen. Okay, from formula. First off, if a compound only contains CH, we call it a hydrocarbon. Okay. Propane you use in your grill is a hydrocarbon. That's all it is. It's made up of hydrocarbon. Maximum number of H's saturated is 2n plus 2. All right, we already looked at that. Like C3H8 would be saturated. I do just other examples there, just like I did here. The big thing is, what if we bring in other atoms, heteroatoms, non-carbons? For example, Prozac. What do you do with these other heteroatoms? How do they count? Here's how they count. If you see a halogen, everybody know what a halogen is? Guys on the far right, well, not the noble gases, but bromine, iodine, etc. Halogens count, when you're doing this, count as an H. When you're doing your DUS. So there's 3. Let's get rid of those. Do it how you want. I can erase here easily and change this to, that's like 3 more H's. Change that to 21. Oxygen you just ignore. Nitrogen, you subtract an H in the formula. So if we get rid of that, we subtract, and this goes down to 20. So this formula can be turned into this from the manipulation I just described. Once we turn it into this, now we can use 2n plus 2. 17. What's saturated for 17 carbons? 2n plus 2 would be
34.
36. 36 would be saturated. How many are we missing if we only have 20? 16. Good. This is what?
There's eight.
And what do you do with that 16 number to get your final DUS? Cut it in half. 16 goes to 8. 8 is your answer. Prozac has 8 DUS. We just did it from formula. Now these, I'm not going to go through why you count, negative, subtract, add. Oxygen, though, I can show you easily why. If we have, don't write this down. Just let me show you. That's totally saturated, right? C2H6. 2n plus 2 is 6. It's there. It's a saturated compound. No pi bonds, no rings. If I just add an O here, it ain't going to change the number of hydrogens because I can just slip in an O and the number of H's doesn't change. But if I want to slip in a nitrogen, I've got to have something to fill its valence. So I'm going to have to add an H. Don't get confused. I just added an H. But over here I said subtract one. Because here I'm looking at structure. You subtract from formula. Because the formula had to have an H in there. And if we're going to all carbons, you get rid of an H. Don't get confused. It's all here. I'm just telling you miscellaneous things. You got to read. Let's look at the structure of Prozac. Does it really have 8? Let's look at structure. That's in your workbook. It may also be on the drug sheet in the syllabus. Yeah, it's also on the drug sheet in the syllabus. Right here, Prozac. How many DUS do you see from structure? How many rings? 2 rings? How many pi bonds? For us right now, how many double bonds? Each double bond contains 1 pi bond. So it's 6 pi bonds and 2 rings for a total of 8. So we did it from formula. We can also see from structure. DUS is something to help you when working with structures. Okay? It's meant to help you. Good thing to organize your some thinking. Resonance. We really covered that. Yeah, we did a little resonance arrow. Maybe do resonance structures. All you're moving is what when you go from one to the other? Yeah. Don't move any atoms. Move atoms where you got different compounds. Functional groups. Same handout as DUS. Let's look at those a little bit. Standard bonding, yeah? The functional groups are different arrangements of atoms, common arrangements, that are all going to have standard bonding. But it's like pre-built starting blocks. I mean, you ever do anything, you got some pre-built stuff? Functional groups are just pre-built. They also have names, so when we look at structures, we can identify this particular arrangement. Let's look at them. Up top, these are hydrocarbons. Okay? Now, this came from the textbook by Smith, not even the one of right? Klein is the official one. I pull things from other textbooks as well. By using Smith textbook, we used to use it a few years ago. These are the functional groups you need to know. Your textbook may include one or two more. Your textbook may be missing one or two of these. Okay, first here is hydrocarbons. By the way, anytime you have a table here, please look at headings. What's all here? Now, I don't know exactly with this one, but for example, I can imagine you guys going the whole semester and never realizing that these are hydrocarbons in this box here. And I would point out to you, well, what did they say at the very top? Especially my handouts. I put headings there that are meant to be helpful. And you guys seem to gloss over that too quickly. You got to first say, okay, what am I looking at here? These are hydrocarbons. Okay, for next, what are types of hydrocarbons? Well, alkane, alkene, alkyne. Okay, alkanes are saturated. All right, we'll learn more of this going forward. Saturated, there's no pi bonds. Now this is a condensed kind of formula. It's not, they're not saying it's C2H6. They're giving you a little information in here. You also have to be careful. Is this H bonded to this carbon? No, the H's are really on this side. But this is just sort of so it can be typed. You've got to be aware of this. All right? And know that what is a reasonable bonding here. Alkene, enes. Enes have the double bond. And so there's one pi bond there. We'll talk more about it. Alkynes have carbon-carbon triple bond. Okay? And right now this is carbon-carbon. Carbon-carbon. Aromatic compounds, there are lots of them. The granddaddy is the benzene ring, 6-membered ring with 3 pi bonds. That's the granddaddy of the aromatic. Now, does it say about aromatic? I had to add something here. Yes, this is the definition of aromatic. Just because it's a ring doesn't mean it's aromatic. It has to be a ring and p orbitals. Okay? Down here we have functional groups that contain carbon Z bonds. Now there's no Z on the periodic table. Z is just sort of a generic. It's really meaning other than carbon. Something other than carbon. Like maybe a carbon-oxygen bond. All right? Basically heteroatoms now. Let's see how far we can get through these. Alkyl halides. Generic structure R. There's also no R on the periodic table. R is generic for alkyl. And alkyl is like alkane. Usually just carbon group. Okay? And again, a lot of these things, you're rushing to write that down right now, etc. We're going to be saying these things a little bit over and over. Okay? It's not like this is your only time to hear this. Say it today, we'll say it next time, and okay? So you don't have to be so, I gotta get this, I gotta get that. All right? It's here. Go home and look up alkyl and just, okay? So we have a carbon group bonded to, well, X is another generic. X is typically halogen. Carbon group bonded to halogen. A precise example would be like the methyl group bonded to bromine. Of course, these H's are actually on the periphery here. They're not bonded to bromine. All right? So this would be an alkyl halide. Alkyl halide. If the R group is aromatic, it'd be called an aryl halide, because we got an aromatic halide. The YL is sort of when it's a substituent. aromatic with a halide. For example, the benzene ring bonded to the halide. Alcohols. This is where you have a carbon group bonded to an OH. We showed one earlier. They're showing methyls with everything, so a carbon OH. We did a Lewis structure for that. We called it methanol. One carbon meth, OL ending. We're not doing nomenclature right now. You can also call this group a hydroxy group. An ether, as we said earlier, is where the oxygen's bonded to two R groups. Not one, but two. It's an ether. The OR is called the alkoxy group. This is hydrogen oxy. This is alkyl oxy. Hydroxy, alkoxy. If we have R group bonded to a nitrogen, it's going to be called an amine. Now in this case, the nitrogen can have two R groups bonded to it, well, 1, 2, or 3. All 3 bonds to nitrogen can be R groups. Regardless, they're all amines. If one carbon group is bonded to nitrogen, it's called primary. If 2 carbon groups, it's secondary. If 3 carbon groups are bonded to nitrogen, it's called tertiary. So like a tertiary amine, a primary amine. Oxygen, you don't do it that way. 1 R group is one name. 2 R groups is a different name. 2 R groups here is the same name, but it's just classified as secondary. Right? Thiol. Well, this is sulfur. Sulfur bonds like oxygen. It's analogous to your alcohol. Okay? These are analogous. Thiol. Sometimes also called a mercaptan. Mercapto group. Maybe in biology you call it a mercaptan. Sulfide. This is analogous to an ether. It's just oxygen sulfur. Sulfur makes 2 bonds, 2 lone pairs. Sulfide. On the other side are groups that have functional groups that contain the carbonyl group. C double bond O is called carbonyl. Some people say carbonyl. I always say carbonyl. Carbonyl is not an exact functional group. Name the functional group, carbonyl will never be the answer. Carbonyl is part of functional groups. If the carbonyl has 1 R group and 1 H on this carbon, it's called an aldehyde. If the carbonyl has 2 R groups on the carbon, it's called a ketone. Carbonyl with 1 R group and then an oxygen here with an H, an OH, that's a carboxylic acid. And this hydrogen is acidic. This is one of the most acidic functional groups. Organic functional groups. Okay, we're out of time today. We'll finish this list up on Wednesday. Please be looking at these, see what types of questions you have about functional groups. There's a couple of other ones I added at the bottom that I want you to know. We'll mainly be looking at hybridization starting Wednesday. Hybridization, you have the outline. Have a good Monday, guys.